Thank you. Can you hear me? Yep. Okay. Let's see. My name is Fredrik. I work as a freelance contractor based here in Stockholm. One of the projects I have the good fortune to work in is called the Cryptech project. It's really fun stuff. I hope you will find it amusing as well. To start off, I have to tell you that not all my slides are made by me. I managed to steal some from Randy Bush, who is heading the engineering effort of the Cryptech project. So his slides look like this, and my slides look like that, okay? And well, this talk is a bit about trust. So I think I'm off to a bad start because I just gave you a reason to not trust me because he didn't actually make this slide. So I'm going to start with the origins of the project. It's sort of from the IETF, but it's not really an IETF project. But as I understand it, this is Randy's slide, not mine. That's one of the hard things for me when talking is to talk about someone else's slides or stuff. But I'm going to try. So the origins of the project were that a lot of people in the IETF, you know the IETF, the standardization body, making lots of the protocols we use on the internet, they have been making, you know, plain text protocols forever. And then we all learned that there are people looking at like everything on the internet. So a lot of these people in the IETF were really upset, and there was the IETF has since taken a stance that they will mitigate pervasive monitoring on the internet. What's the way to do that? It's encrypting stuff. So the IETF decided we need to encrypt like everything, but it doesn't really end there, because when you have encrypted your stuff, you have to keep your crypto keys secret, right? And how do you do that? You use hardware security modules. These come in very different form factors and price. The smallest ones are probably smart cards. I believe there's something we could call an HSM inside all of our phones. It's a, what's the name? I forgot the name. It's a small chip. Wikipedia says it. It's, is there anything important here? No. Okay, so what you do, what is an HSM basically? Oftentimes it's a server. So you take something ordinary and you enhance its protection, you fortify it, you harden it in order to keep attackers away. So some attackers are you know, very interested in getting into your box. The goals of the project, trying to keep it short, is to produce a reference design for an HSM. We are not going to manufacture products. We really hope that someone else will find our designs useful, thinking, you know, wow, I can save a lot of R&D costs here by using these guys' free designs that they put on the internet for all to read. And I can build a product which I can sell. We really hope that happens, because, you know, if no one manufactures this, then we would essentially have done it for nothing. So we're trying to do you know, a good product. It's supposed to be scalable. It's supposed to be secure, composable, like in an open source project that you can. I mean, most people don't compile open source projects themselves, but at least there's a possibility. If you really want a small part of an open source project but not the rest, you can just compile it yourself without the rest. And we want the same thing here. We want it so that this HSM you can actually sort of build from scratch yourself. How do we establish trust in this HSM? I mean, why don't people trust the HSMs you can buy off the shelf today? I mean, from my point of view, it's because we don't know what the HSMs do. we don't get access to the insides of an HSM. HSMs are black boxes by design, and the manufacturers keep their stuff really close to their heart, not mine, although I'm the one who buys it. So we think that we can, or the only thing we can do to establish trust in what we build is to be as open as possible in many different ways. I'm going to touch on some of them, but not all. So these are how we are trying to do this. We will be transparent in everything we do, everything we sort of deliver, everything we publish will be under either a BSD license for code or a, let me see, I often get this wrong, Creative Commons license. Sometimes I say common criteria, and that would be embarrassing. Creative Commons license for stuff like this presentation is actually Creative Commons, so steal it if you want. We actively seek review of what we do. If anyone is interested in this or knows someone who's interested, please have them look at our stuff and tell us where we've done it wrong or where we can do better. For the engineering effort, we have made a real effort to find people from different parts of the world. We have, actually he's in the room, Joachim, please stand up. That's Joachim Strömbergsson, he's part of the project. Are you all awake? Everyone that's not Joachim Strömbergsson, stand up. You're not listening to me, only a few people stand up. Joachim does Verilog, which is like the programming language for FPGAs. We have people in Boston doing hardware adaption and interfaces. One of the first interfaces we have for this is PKCS11. That's a standard interface for accessing hardware security modules and smart cards, etc. So that sort of instantly makes this usable for people. You can more or less drop it in. It's sort of hand waving to say drop in, but you can more or less just drop in this HSM where you had some other HSM previously and use it. TRNG is a true random number generator. We get advice on how to build that from Germany, Russia, and the States. I'm going to be talking quite a bit about TRNG soon. Hardware design and build in Stockholm, that's me. And we one of our first use cases that we are trying to deliver is DNS-sec support, and we have Jakob Schlitter, who was part of the effort to sign the DNS route, leading that effort from Göteborg. Randy Bush lives in Tokyo, so he does the engineering coordination. All of these people have actually provided funding for this project, some of them quite substantial funding, even though we're sort of underfunded. So if you have deep pockets and like this stuff, then get in contact with us. I don't know what these private donations are. There were no one giving me beer yesterday. So this is another view of an HSM. This is what we produced on one of our first design meetings. We had this. We came up with this layer cake module. So just so that we all sort of agree on what an HSM is, what you would have is an application running up here somewhere on your server that wants to do crypt operations, but you don't trust your server to have the keys. So you have the server use an API to access the external hardware, the HSM, to do the crypto stuff. So what we are sort of making designs for is the green and blue layer. That's the hardware part of it. And then we're making open source for stuff up here at the moment, PKCS11. Maybe we'll get to doing open source up here. I'm not sure. I mean, these are generally existing applications. So I think we will do mostly in yellow and below. Okay. FPGAs. Everyone knows what an FPGA is. It's a field programmable gate array. and lots of people think these are cool. Unfortunately, I can't really talk to you about them because I don't know very much about them, so I would just make a fool of myself. So I won't. Sorry. I'm incredibly happy to be ahead of schedule because one of the hardest things for me when doing presentations is keeping on time. So I have a couple of these slides so you can all see if I'm on time and we can decide together if I need to skip some part. But as it is now, I'm actually ahead of time. So an HSM, this is another one of our design documents or working documents. This is not the design itself. It's a working document detailing lots of different parts of what our HSM will be. We have the FPGA, we have an ARM CPU, we have a real-time clock to keep track of time, and we have RAM and so on and so on. So a lot of these would actually be very fun to talk about. Some of them I could talk about, some could Joachim talk about, or someone else could talk about them. A lot of them would be hugely interesting to talk about, like the tamper subsystem in itself would be very interesting. But we don't have the time, and I can't talk about stuff that I haven't built, so I'm going to talk mostly about this little box here, entropy sources over there. My primary contribution to the project this far has been working with building the true random number generator or a part of it. Because now we actually need to talk about what is entropy versus what is random data. And we need to agree on how we build a good random number generator. A random number generator can't, or I mean, this is how you generally build them. You have entropy sources. Entropy is like, I think a lot of people see it as the same thing as random, but that's not true. Entropy is something unpredictable, but it's not necessarily good. Think of it in bits and bytes. Let's say that entropy is something random, but maybe it's not 8-bit random per byte. Maybe it's just 1-bit random per byte, or maybe it's 6 bits random per byte. Maybe it's not always the first 6 bits, but there's sort of, if you make calculations, you realize that it's about 6 bits per byte that is actually random in your entropy. So you can't use something that only has 6 bits per byte in cryptographic operations. You need to do something to make sure that you have 8 bits per byte of unpredictable data. So this is how we do it in the Cryptech project. We have a number of entropy providers here, entropy sources and entropy providers. This is a module in the FPGA. We don't need to dive deeply into the FPGA part of it, but this is basically it. We have a noise sources over here producing sort of hard to gauge number of bits per byte of entropy coming in here. This is the one I built, the avalanche noise entropy source. We have another ring oscillator. This one is internal in the FPGA, which is a plus in itself because, well, one of the crucial parts about your random numbers are that no one else are supposed to know what they are. So if this is the input that will produce the random numbers in the end, you have to keep these secret and unpredictable, and you can't let other people affect the entropy sources, or at least not too much. Because what you do is you take your entropy sources, you stuff that into a mixer. In our case, the mixer is basically SHA-512. So you take, it says here, it's like 1,024 bits, 1K bits. You stuff that into SHA-512, you get 512 bits out. At this point, we sort of really hope that no one can know what they are based on being able to observe the entropy sources over here. When they are mixed together, or, well, sorry, if you can observe one entropy source over here, when it's mixed with a number of other entropy sources and go through the mixer, we hope that no one will be able to know what's in there anymore. Because the output of the mixer, that's actually used as the seed for a CSPRNG, a cryptographically secure pseudo-random number generator, which in our case is currently the Cha-Cha cipher. It's a stream cipher, meaning you put 512 bits in, and you can produce an almost arbitrarily long, I mean, it's multiple terabytes at least, long output that will be totally unpredictable to anyone who doesn't know the 512-bit seed. Okay, so do you follow me? Is this sort of clear? Lots of people nodding. Excellent, excellent. When the Cryptech project started, I already had this idea that I would build a random number generator for my Raspberry Pi. How many people have had that idea? It's a very common thing. I see like 5 hands at least. It's a very common thing. Lots of people build hardware random number generators. I myself, I did it because, you know, it seems like fun. It's a cool thing to do. And how hard can it be? Yeah. So I had already started looking at what hobbyists do when hobbyists build random number generators, because that's exactly what I was at the time. I was doing it as a hobby project. Most people use avalanche noise. A little bit later on, I will make at least an attempt to explain what avalanche noise is. A lot of people use that. Some people use op-amp noise, and there are people using thermal noise. I'm sure there are other variants. One that comes to mind is people take radioactive components from smoke detectors and put that next to a CCD and tape it around so it doesn't get light from anywhere else, and then you look at the output of the CCD and see when there are, you know, radioactive decay. But yeah, we had that discussion and realized that we're not going to be able to make products that have radioactive materials in them, because then it will be, you know, you can hardly get lithium batteries on airplanes, so that would sort of inhibit people from using it. So I had done this pre-study myself and was almost about to start building it, and then comes the Cryptech project and says, we're going to build a really good random number generator. And I'm like, wow, great. I'm going to learn from a lot of knowledgeable people over here who will show me how to build a random number generator, and I'm going to build the best random number generator for my Pi. And I was really happy about that. So I told people about this, probably over beers. And then the next day, someone comes up with the idea that you've already started. Why don't you build it? Okay, so I'm flattered and I'm stuck with building it. So yeah, okay. So then we started having discussions in the project of what kind of random number generator to build, and we had some other ideas, like you have a RAM circuit, an SRAM circuit. You turn it on, you write stuff to it. Doesn't really matter what you write something that's sort of random maybe. Then you turn it off, and almost immediately you turn it back on. Then some of the bits will have changed in memory in hopefully unpredictable way. That's a fun idea of how to build a random number generator, but we got some serious pushback from friends of the project for that idea, so we didn't really pursue that. But the good thing with our design is that you can actually have many sources. So maybe we will come back to building other kinds of sources that you can enable or disable at will as well. Another thing with the area of random number generators are patents. Lots of ideas for how to generate random numbers are patented. A good thing about avalanche noise is that it's a really old idea. So we found at least one patent that covered a sort of an avalanche noise and more, and this patent had already expired. So then I'm not giving legal advice here, but then we figured that it's probably okay to do avalanche noise because it's covered by an expired patent anyway. So this is electrical schematics for an avalanche noise of some guy on the internet or girl, I don't know. This is the basic idea. Is you have a transistor that you only connect sort of halfways, so that this is where the noise will actually be generated. Then you amplify it over here, you amplify it even more over here, and this guy digitizes it over here, and out comes randomness. We have a number of these. You see this transistor that has one leg disconnected is present in all of them. Suddenly, when I had sort of come to the conclusion that, okay, it's an avalanche noise source I'm going to start with, suddenly there was an article about Cryptech in a German magazine that I forgot the name of. So a bunch of Germans came to the mailing list and started contributing. One of them was called Benedikt Stockebrand, and he had already built this. He started out a bit earlier than me, or he was better at getting going. So he had already built an avalanche noise source, and he contributed his design to the project at a very good time. So it's very similar to all the others. Over here we have this unconnected transistor, amplification, more amplification, and I added this digitizer circuit over there. Benedikt, let me see. Here's from a CAD program. Here's a drawing of Benedikt's board. And here it is in reality. He sent me one. Thank you. So Benedikt's idea was to build this with only through-hole components. Through-hole means the legs of the components go through the circuit board, and you solder them on the other side of the circuit board. That's old school, and it's much simpler to do than surface mount technology. Benedikt really made an effort to design his board such that other people would be able to build it, physically be able to mount components, etc., and also to test it. He has lots of test pins here. Really good design for testing. Thank you again, Benedikt. Considering through-hole components, we already knew that we will have a really top-of-the-line ARM CPU, and we're going to have an FPGA. So the ship had already sailed on surface mount for us. So it was sort of clear that we wouldn't benefit from having through-hole components. People won't be able to solder our designs at home anyway. You're going to have to order it from someone who can do it professionally. So I started out making prototypes for randomness. Here's the first one. Starts out on one of these little experimentation boards. This one looks sort of all right? But then you add all the wires you need to connect it to your MCU or your Raspberry Pi or something, and suddenly you have this mess on your table. I can't really take that, so I had to make a special board. Revision 1, revision 3. I haven't really physically produced all the revisions I have here. Revision 2 was lost in history. It was probably an attempt to rearrange it or something, and I didn't really go with that one, so I came to revision 3. At this stage, I'm using the MSP430 CPU. Nice little 16-bit MCU. Can really recommend it if you want to step up from Arduinos. You can go to MSP430. Excellent. I'm 5 minutes ahead of schedule. What is avalanche noise? I wish someone else could tell you. as far as I've understood it, or I mean, I know how to produce it. You take a PN junction, that's another word for diode, basically. So you take a diode. Diodes make sure electricity can only go one way through the diode, right? So you apply voltage from the other way. So the diode blocks. The diode makes sure that nothing gets through. But then you increase voltage until you get to the breakdown voltage of the diode, where it will actually start letting electrons flow the wrong way through the diode. And as far as I've understood it, what avalanche noise is, or avalanche breakdown, is that at some exact point in time, the reverse flow of electrons will start. That will be unpredictable. And then there's like one electron jumping over to the other side. That opens a tunnel for electrons. I mean, this is Star Trek. So a bunch of electrons rush over to the other side. And that brings down voltage. So suddenly the diode will be able to resist again and close the tunnel, so no more electrons get through. And then the cycle repeats, actually. So if we have my schematics, we have the noise generator here. We have the raw noise label here. So what if we look here just to see what avalanche noise is? Using an oscilloscope, we have here 100 millivolts per division. Division is these squares here. So we have like 1, 2, 3, 4, 500 millivolts peak to peak here. Can you see that? Yeah. Okay. So this is a snapshot of avalanche noise. We have, I believe this is, this is how I've understood it. This is the breakdown here, and then it recovers. Then you have breakdown, recover, and so on. And it's clearly random, right? We can't see a pattern in here except that it goes up and down. The next step of the circuit is amplification, because a couple of 100 millivolts is sort of you can't really sample that easily. So you need to get it to something easily read by the microcontroller, if we put it that way. So if we add another probe over here at the amplified test point, we see this. The blue is still 100 millivolts. The yellow is now 1 volt. So you see, it's not only amplifying, it's also inverting, but that's irrelevant for the circuit. And we lose a lot of details when doing this, as you do when you amplify if you don't have really good circuitry for that. But that's not important, because this is actually what we want. We want to see we want random events that we can read with a microcontroller. So we have a couple of slides on that. So when you want to extract the entropy from your avalanche noise, what do you do? Given the slides here, let's go back. Given this, up and down motion, it's sort of natural to think that I'm going to use an ADC, an analog to digital converter, to just read the level, and that's my randomness. What voltage I have at a given point in time should be random. Yeah, you could do that, but then you would need to account for lots of changing parameters like temperature. The voltage of your avalanche noise will change, and the required voltage to achieve the avalanche breakdown will also change based on temperature. And even worse, I think, is component aging. So when components age, when these little transistors age, they will start to change, requiring perhaps more voltage to get a breakdown effect. Or, I don't know, I haven't done any, IKEA tests. I haven't done any of these things that open and close your cupboard door 10,000 times. So another way to do it is to base it on time. If you think, if you have a clock running really fast, like, I mean, microcontrollers are cool, 16 megahertz. That's incredibly low, right? Compared to today's cell phone, etc. But it's actually something happening 16 million times per second. And for a human, that's like that's a very small part of a second. And that's just 16 megahertz. So in a microcontroller, you can easily have a clock running at your base CPU speed. All of the microcontrollers I've encountered have this, at least. I'm sure there are those that don't, but so you have sort of like a multitasking thing, that you have a clock that will increase by 1 by every clock cycle. So what if you wait for the rising flank? Let's see, is it far to go back? Here we are. A rising flank is this, where it goes from low to high. So we have one here, we have one there, we have one there, and there. What if you wait for that? And as soon as you see that, you take the counter value. And what I do then is I take the least significant bit of the timer, the counter value, because the least significant bit will toggle between 1 and 0 for every clock cycle. So like 16 million times a second, it will toggle. So just take that. And the biggest reason for doing that is because what we believe, our theory about component aging is, and also of differences between individual components, because these transistors are, they're not exactly the same, so they're going to have different characteristics. So, but our belief is that while component aging will affect the avalanche breakdown in our transistors that we use, it won't affect the quality. So it might affect the frequency, but not the quality. So basically, the entropy source might get slower and eventually actually stop. But the quality, as long as it produces something, the quality will remain the same, is our belief. So that's how we do it. And then you can sample using different methods. Let's see. Digitization. Going from this amplified signal to what you sort of get in the processor. You have an analog signal in. You use something called a Schmitt trigger. Hang on a second. To make it a digital signal. And the Schmitt trigger works like this. It's a thing with hysteresis. So look at these two white lines here. So the thing is, you have a low and a high watermark. So a Schmitt trigger will not, here, when you have this rising flank of the blue curve here, when you have the rising flank, when the rising flank goes above the top line here, the Schmitt trigger will say, okay, now we have a 1. It will stay at the 1, not just until here, but until you go below the lower watermark. So if you would only have one exact distinct level where you say, it's a 1 if you're above that and it's a 0 if you're below, if you had the input being more or less exactly that level, you would get an oscillation of your readings, although there are no perhaps real change in there. So you use a Schmitt trigger. So this is basically what it would look like. This is just a 4 megahertz signal to sort of illustrate this sampling frequency, or if you sample at 4 megahertz, this is how often you check if there's a change in the voltage level of your digitized input here. Okay. Timekeeping, 25 minutes. Let's see. I'm 1 minute ahead. That's still good, right? So now I have this circuitry where I could start extracting data from the avalanche effect. So my circuit at this time was a bit slow. It only produced like 10 kilobytes per second. And if you're going to do statistical analysis of random data, you actually need quite a lot of data. So it would actually take, dieharder is a popular tool. Dieharder has this peculiarity that it reads data, and if it doesn't have enough data to use for a test, it will start over from the beginning. So you're looking for patterns in data, and then you're reusing data. How does that even work? I mean, it's always going to find a pattern because, you know, it starts over. So we used different tools to check the quality. Ent was the one that turned out to be mostly useful, actually, for these quick tests where you don't have like 16 gigabytes of data to give to dieharder. Or I don't remember, maybe it was even more, like 40 gigabytes or something, to not have it restart. So if you want to know if something's wrong with your circuit without waiting for a couple of weeks to extract a number of gigabytes of data, you use some kind of lighter test that will give you an indication. So the Ent tool implements a number of tests for random data outlined in one of Knut's books from the 60s. The most useful part of it, in my mind, in my opinion, was the chi-square test. Chi-square, I'm going to talk a bit about that, so first I have to hopefully make you understand what it is. As a not native English speaker, I couldn't produce a sentence like this, so I'll just, read it loud. A test of goodness of fit establishes whether or not an observed frequency distribution differs from a theoretical distribution. You got it? This is the formula. I can't read this, or I mean, if my life depended on it, I could, but it's not my preferred format of information. Because this formula can also be shown like this with C code. This is, sorry, say again. Yeah, he's the mathematician, right? Who prefers this format? I see 4 hands, 5 maybe. Who prefers this format? Lots more hands. Okay, so chi-square works like this. You take, let's see, doing math in my head on stage, another bad idea. Let's say you have 256,000 bytes of what you want to see. Are these bytes random or not? 256,000. So if it was a perfect distribution of all these characters in the byte stream, you would have 1,000 of each byte value, right? So what you would get then is, let's see. This becomes too hard to do on stage. Anyway, you would get a low chi-square score if you had the perfect distribution. Maybe it's even 0 or 1. Someone with a calculator can do that. But when there are more or less of some byte value than you would have expected, then you start quickly getting a higher chi-square score. That's the whole point. So you see, that's the square portion of it. Is you take Cx is the expected number of value x, and then you check how many were there. Okay, so there's a difference between the expected and how many there were. So you increase your total chi-square score with the difference squared. So if you have a perfect distribution, you will get a low score. If you have strange stuff in there are 100 more of byte value 0 or 500 more or something, you would get an incredibly high chi-square score, even if all the other byte values are uniformly distributed. So from this chi-square test, we could see that something was not really working well with my random number, with my entropy source. So I started trying to figure out what can I do to improve this? What's the real problem? But I figured that I couldn't really see that from just looking at the chi-square score, because the chi-square score is like, it's distilled down. It takes huge amounts of information and condenses it to a small value that can be low or high or good. So I had to look at the information that was eventually becoming the chi-square score. So I started looking at timer deltas. You remember I had this timer running that I sampled and used only the least significant bit from. But I figured, what if I actually get the whole counter value and plot that? So I got this plot. It actually didn't make me much wiser. But you can see some strange things here. Look at this. The y-axis is logarithmic, so it's not really important that what you see down here, because this is like no occurrences at all actually compared to what you have over here. This is 10 raised to the power of 6, so this is a lot. So particularly these two being much higher. There are two counter values that are massively overrepresented in the readings of, I think it's 1 million counter values or something, or 10 million, I don't remember. I compared that to what Benedict had on his design. I modified it so that I could get timer values or timer deltas from his design, and he had this distribution. It's sort of wider between the steps here, because I was using a timer running at 16 megahertz or whatever, and he was using a busy loop. So in his case, this is actually the number of iterations his code would run through the loop until it saw the next rising flank. So that's why there are gaps. But the general slope of it is there. But this looks more even, although it's not perfectly even. I did more tests, making modifications to my extraction code, trying to extract the entropy in different ways. And more tests. This one is I can't express it mathematically, but it's not good. Even more tests. All of these images are actually from the email archives, because some people sit in their room and try to make something perfect, and then they tell the world. I have no problem with telling the world when I don't do perfect. So all of these are from emails I sent out to the whole project mailing list and saying, oh, I got this result now. It still doesn't look very good. And sometimes it gets really bad. So finally, I had something that looked like it this could possibly generate good randomness, because at least it's the expected slope here, which is how do you say that? Exponentially decreasing probability of flank being later and later, if you put it that way. That's what we see here. There are lots of flanks on a high frequency, and then you have an exponential drop-off of number of flanks being further and further apart. That's what we're actually looking at when we see this slope here. Okay, so now I had a graph that looked good, and my hardware had evolved to this. Note that it's actually on a Raspberry Pi, which was my goal from the start. This is the same board, but from the other side. So I'm using 15 volts. Right. Another thing, the good-looking graph said it's better looking but slow. I was still using 10 volts, so I made this 15-volt revision. Had 2 charge pumps cascaded instead of just one, so I got 15 volts. So then it's faster. But, well, this board didn't really produce good graphs either. I had lots of experimentation with this MSP430 CPU to try and read out these values without introducing defects in the values because of the technology I use to read them. Lots of those. So finally, I actually gave up on the MSP430. I think the main problem with it, the thing that made it impossible to do something really good with that particular CPU, is that it did not have what's called double buffered registers or memory addresses for reading data from timer capture value. Meaning that, I mean, I would have this circuit that produced new rising flanks about 1.5 million times a second. And so a double buffered memory when reading these values would mean that the CPU would place a distinct value in one register and tell me, you can read that, and it won't change while you're reading it. Because if I need to write it again, I'll write it over here, not where you are. But the MSP430, at least in the 2000 series that I was using, didn't offer that. So it did not have double buffered capture memories. So however I tried to do it, there was also always a risk that the CPU would actually write stuff to the memory offset where I was reading at that exact time. And that would, of course, introduce bit errors that I couldn't detect. Or, I mean, the MSP430 way of doing this is actually to disable capturing and then do a reading and then re-enable capturing. But that's just too slow. It's really slow. So I gave up, made a new design. This is based on an ARM CPU, MSP430, STM32. This is, I believe this is 401 and M4. Can run at, I think, 80 megahertz. So suddenly I'm sampling at 40 megahertz. That's fun, or more fun. So again, an illustration. Think of all these yellow here is a moment in time where the MCU will actually check if there has been a change from low to high. So now we get some much better resolution at this. And, I was always thinking to myself that this will be incredible because half of the time the lowest significant bit will be 0, half of the time it will be 1. But in the end, I've realized that that's not the case. And I think I know why, but I'm not sure because I don't have the instruments to measure at that precision. I suspect that there's actually in these, think of these as the clock cycles of the MCU. If the clock cycles were of perfectly equal length, always, my scheme would work. But what if it's actually not? What if every, say, 30-second clock cycle is actually a tiny bit shorter than the other 31? So then you have a bias suddenly from the length of the clock cycles of something happening 40 million times a second. So with this new CPU, I could actually do DMA-based counter value capturing, which worked really well. You have a buffer, like 1 kilobyte buffer. You say to the CPU that whenever you see a rising flank on this input pin, I want you to take the timer value from this constantly running timer, put it on the first offset in the 1 kilobyte, then automatically move on to the next offset, and so on. So what you get is that instantly the CPU will fill up that buffer with timer delta values for you, or timer values, that I could then extract and make another graph like this. And you see it actually looks really good. So good hopes with that. And we're now at revision 9. And I did this with Reflow soldering, so it's not just a solder pen anymore. It's you use this stencil to get solder paste. It's like a goo. You have solder in the form of a goo that you just spackle out over this stencil to get paste on every little pad on your board where you want to mount something. And then you, with a small tweezer, you put out these components. Like this one, these are LEDs. They're about a millimeter each. So you have a small tweezer and you put those out, and then you shove it into an oven. And I had to buy a separate oven for that. It wasn't allowed to use the house oven for soldering. So this thing here is 0.5 millimeter pin pitch. So that's actually 1 millimeter from here to here. So there are 3 of these legs per millimeter. I like it. Let's see, time, 30 minutes. Let's see. Oh, I'm well over time. This is bad. This is really bad. Okay, hurrying up. We have this platform called the Novena. It's a Bunny Wang's open source, open hardware laptop. He put an FPGA on there. So we built one of these entropy sources that we connected to the Novena to use the FPGA on the Novena for development. Now I really have to hurry up. So this is the Novena. You have an FPGA. Good. Here's one of my boards running on there. Joachim loves blue LEDs, so he got 8 of them. We did more tests. I used this simplistic extraction scheme to extract 1 bit of the time. I found out, I dug deeper in the chi-square and made my own implementation of an analysis program to make these graphs, where each of these small red triangle is a chi-square value of the last 10 megabytes. The green is a accumulated total chi-square from the start of the file. These lines, or if you call it lines, this is individual byte values and where they rank in an index from 0 to 256 in most common byte value. So what's strange here is these, how the black and the purple sort of gets up to a certain position and then remains at that position throughout the file. Bad stuff. Here it's even more evident. You have this black thing here. What is it? Let's see. I can't see. It's one of these inspect values. That's the black one. That's definitely not good. I mean, this is not supposed to be patterns in random data. So what you need then is whitening. I mean, I explained this difference in clock cycle length. So you have to accept that you can't really read data perfectly. So you have to compensate for that. And I'm a bit sad about it because in some way it's removing details. You're obscuring the data. So what we did here is actually to take 2 samplings, XOR them, get 1 bit. Take 2 more samplings, XOR them, get 1 bit. Use von Neumann algorithm to remove bias from these. And then we get a good score. Then we have 40 gigabytes here, which passes all these tests. Those chi-square, hurrying on. TRNG recap. Okay, we're going to do this really fast. This is the same picture as before. Here's lots of bragging numbers about our TRNG. Joachim wrote these. Online testing and stuff. I went backwards now. Online testing, support for adding more entropy sources. You can exchange SHA-512 if you don't like that. Here's cool stuff. We can generate about 500 megabits per second at 50 megahertz. I think we're actually running a bit faster than 50 megahertz. This is in the FPGA, the 50 megahertz. So we're running even faster than that. And if someone says, we want 4 gigabits per second, we just instantiate more of these cores, the bottom here. You instantiate more cores and run in parallel, which is like the power of the FPGA. So we're testing these using all the tools. We're actively trying to engage third parties to do testing. We're kind of successful with that. Project status, we did a workshop this summer. We actually have DNSSEC signing working with the Novena. Our next step is to build what we call the alpha board, which is this picture again. This is stuff we want in the alpha board. This is the same thing converted more to like a schematic with components. This is circuits we want, different integrated circuits we want on there. This is the dev bridge board, which actually has about 2/3 of the alpha board. And as you can see, this is a photograph. It's not Photoshop. So I actually have this with me. You can look at it. I invite you to come see me and have a look at it. This is our current status. We have the big arm, the random number generator, master key memory. We have tampered MCU here, which will wipe the master key memory if the panic button is pressed. We're like 6 engineers in the project that meet regularly, and we had this great fight on one of our meetings where we couldn't decide, we couldn't agree on what tamper sensors to put on the board. So the only thing we could agree on was to have a button that you could press to simulate tamper events. But then we have 8 inputs here. So we're like setting it up to start building tamper detection circuits based on temperature, based on light, based on vibrations, etc., which is what you typically do to protect your secret keys you store in your HSM. So this is the back of it. So this is the FPGA emulation. This connects to the FPGA on the Novena. Okay, almost there. So who said it's awesome? Actually, Edward Snowden. Let's see. No, I don't have the time. I would love to try and show you this, but it's on YouTube. There was a screening of the movie Citizen 4 at the end of the IETF this summer in Prague. So at the end of that screening, there was a surprise session where Snowden participated using video link. And in his talkings, he suddenly suddenly turns and says, "Oh, the Cryptech project, what you're doing is awesome." I had to have that here. Okay, I'm done. They told me I have to take this down to prepare for the next speaker. So everyone who wants, photograph this real quick because it's going offline in 30 seconds or less.
But we'll put them all online, right? You give us the presentation,
yeah.
we
Sure.
put all the presentation online.
Yeah.
So people can go through it and see it. All right.
Questions?
Yeah, I mean, you want to have a lot of different entropy inputs.
Mm-hmm.
And one of them will be this.
Yeah.
How many more?
Not sure. I mean, we have to prioritize what we work on. So I would personally like to play with a couple of more, but you have to get the most bang for the buck. So maybe I will. It's wiser definitely for me to focus on making this alpha board first.
Yeah.
So if there are volunteers, just come speak to us.
I'm going to guess there's going to be a couple of questions from this audience. Yeah. There's a bunch of people who want to ask questions.
Do you have any idea how much it will cost in the end?
Sorry, how long?
How much it will cost in the end?
How much the end thing will cost? I haven't really done the math, but I would guess that the bill of material cost is like, say, $200. So if you pay someone to build it, you end up at $300. And the traditional HSMs easily costs, or many of them cost like $50,000.
And I have a question of conscience. Your conscience, is it clear, or have you hacked your Rigel scope for higher bandwidth?
Sorry, I missed that question.
Your Rigel scope you were showing
Ah,
on the
ah,
slides. Yes.
ah.
Have you hacked it?
No.
No, that's good. Well, the next one, have you tried a germanium diode instead? It
No.
should use lower voltages, and you should have less pumping to get it to work, and a good noise anyway.
We tried proper Zener avalanche noise diodes, but it seems like manufacturing of those actually strive to get less noise, and we want more noise. So the best way to go seems to be cheap, off-the-shelf standard transistors. They actually have more noise.
You mentioned something about reviews, like peer reviews of your designs. Do you know if all parts of the project are being reviewed by somebody? Or is there some specific part that needs to have more attention, get more reviews?
Well, we do get some people giving quite a lot of review on the list, but I can't really tell if all parts are being looked at or just some parts. So any part you want to look at, just please come see us at the tech mailing list and talk about it, and we'll set it up.
Would you say the community is warm and welcoming?
Sorry.
Would you say the group is warm and welcoming?
Yeah. Anything else?
Will the random number generator be exposed for just general system use?
Well, the output of the TRNG will. Probably not the entropy source. We will have a test mode where you can get data directly from the entropy source. But you're not going to build or buy this thing for $300 to get to what you can build for $10.
Sure.
So, I mean, instead, please build one of our, or get one of our reference designs, or not reference designs, but the prototypes I've been doing. I mean, all the schematics for those are also deliverables from the product. So I would rather recommend that you build yourself a Raspberry Pi entropy source if you want the entropy itself.
Sure, thanks.
How would you know how much entropy you actually get out of it? I mean, how would you're talking about pulling some entropy out of it and using that for a pseudo-random generator. But, eventually you run out of entropy. You can't pull as much as you want out of it.
But it's hard to determine how much entropy there actually is.
Yes.
So what I have been doing is applying tests actually meant for pseudo-random number generators, meaning I've been applying tests that try to test that something is good random data to the entropy source.
Looking only at distribution.
Yeah, so if those tests that actually want to see perfect random data, if those approve or nearly approve of the entropy, then I consider it, probably really good.
I'm guessing there are more than one ways of determining if something is good entropy or not.
Probably. Not my field.